and then we'll go over this. Okay, so just by the way, I know Adam passed out the test there. Like I said, make sure you leave your tests behind when you go today. Jeannie wanted me to make sure I collected them from you and didn't let them leave the room. After this, all the tests we use will be different, and I haven't decided yet whether I'll recollect them all after that or not. But anyway, so back to our example here. Blood sample exceeds the meter, so we dilute 30 milliliters of blood with 90 milliliters of normal saline, sterile water. The diluted reading, so after we've added the water, the meter gives us a reading of 282 milligrams per deciliter. Find the actual level. Well, the first thing we need to do is we need to find what dilution was formed here. So the dilution is serum, in this case the blood, to total solution. So our serum, the blood, was 30 milliliters. Our total solution was 90 milliliters of saline plus 30 milliliters of blood. So 30 milliliters, over 120 milliliters. So the milliliters cancel out, and we can reduce that fraction to 1 in 4. So that's a 1 in 4 dilution. Step 2 then is to adjust the reading, and we use the dilution for that. We have a 1 in 4 dilution. The meter reading is smaller than the actual reading because it's diluted. So that goes with the smaller number. Yes, yes. So then we multiply and cross multiply and divide. 4 times 282 divided by 1. This was at 1128 milligrams per deciliter. So the true level in the blood is 1,128 milligrams per deciliter. That's a blood sugar reading. You got somebody on verge of passing out there. Any questions on that problem? Okay, now just kind of maybe a half a step back from that, but to make sure you understand these dilutions. For a 2 in 9 dilution, give 1, the ratio of serum to saline, 2, ratio of saline to total solution, and 3, ratio of serum to total. So I'll give you guys a minute. Let's take a peek at this one. So a 2 in 9 dilution. The dilution is always serum over the total solution. So the 2 in 9 is the third one, the serum to total. So then the ratio of serum to saline, there's still 2 parts serum. If there's 9 total parts, 9 minus 2 would be 7 parts saline. So serum to saline is 2 to 7. Saline to total, well, the total parts would still be 9. If 2 of those were serum, the other 7 are saline, so 7 to 9. So the big thing to remember is a dilution is always serum to total. Now, before I get into the newer stuff for this week, I do want to make a quick mention on scheduling. This class kind of gets the shaft this semester. Next week is spring break. So that means there's no class next week. Well, the week after that on March, was that the 30th? March 30th. Yep, that's Good Friday. Well, there's no class on that day as well. We're off on that day. So on Good Friday, we're off as well. So this class will not meet again for 3 weeks. We will meet, what's that? I can post some videos from last semester so you can keep working on it if you want to try to work ahead. So the next class that we will actually meet is going to be on April, is it 6th, I believe. April 6th will be our next class after today. Now, looking at the original schedule, let's go ahead. I actually have some old videos. The choppiness in the videos comes from this computer. This is a new computer that they started using this summer, and the internal microphone is horrible. When I post those videos, those will be old videos from an old class made off an old computer that actually works. I don't mean to sound negative, but yeah, this computer is the issue with the videos. But yeah, I will make sure I post ones that are pretty pure. Now, again, we're still going to lecture on that material, but I might have to move through it a little quickly just to get through everything. Now, just the original schedule that Jeannie posted. April 13th is lecture. And then she had the Unit 3 test posted for April 20th. But as we look ahead from there, there's April 27th. And then I believe it's May 4th. Oh, that was Unit 2 that we just did. May 4th and 11th. April 27th will be Unit 3 test. Or sorry, April 20th. Sorry, April 20th is Unit 3 test. Yes. So we will do the Unit 3 test on April 20th. In order to get through the material, because May 11th is technically our last, or May 17th is the last day of class, which is a Thursday, which means you lose that Friday as well. So we only get 14 Fridays this semester. Well, that's something I wanted to ask. During that last week, if I have to lecture on May 11th to finish the material, I mean, at the very least, I would have to lecture the first hour of class on May 11th. Otherwise, there's no way I'd get through the material. Would you guys rather take the test in the second hour of class? Or would you rather I take the time May 11th, lecture on the material, and you guys take the test outside of class sometime before? It would have to be done by like May 16th in order to give everybody time to gather the tests and send them to me. I mean, you could always stay after class May 11th and take it later that day. But I wanted to leave that option out there for you. Because I know having a lecture on material from 8:30 to 9:30 and then taking a test on it right away, it doesn't give you much time to absorb it. This would be, technically it's Unit 4 and 5 combined, but yeah, that would be the fourth test. If you're in Rice Lake, you can just stop in this room basically any time before 1:30, any day the next week. New Richmond, like I said, you'd have to do it. I'd have it at the library, and you'd have to pick it up in the library and do it at any time. Anytime the library is open in New Richmond. I guess I should leave it this way. Is there anybody? Let's go ahead. It will be open note and open book. That would be it. You will just have a 4th unit test. Unfortunately, it's a standard that's been established, partly by the nursing programs, that tests have to be proctored. Okay. Let's put it this way. Is there anybody that has an objection to just lecturing on the 11th and having to take the test outside of class? Yeah, you can just stay after class and take it right after class that day too. Okay. And okay, let's plan on that. I just wanted to give you that warning. We will have lecture at least for the first hour, May 11th. For those of you that want to just stick around and take the test, you can. If you want to have a few days to absorb it, you can come in the next week. So we'll leave it open that way. So those of you that don't, maybe some of you are only on campus on Fridays, you do have that option of just sticking around and taking the test, or you can take a few days and come in early the next week and take it. I really hate lecturing on something and turning around and making you do a test on it before you have time to do homework or review it or anything like that. There you go. I'll try to make sure that when I put those on that test, I'll make them so that they're fairly simple questions. So they're pretty straightforward. Okay, so back to the material. So far we've talked about these dilutions. What we've talked about is a serum or a pure medication that we've been diluting down with saline. Today what we're going to talk about is what if we already have a solution and we're going to dilute it down further through a dilution to get a lower concentrated solution. So what we're dealing with is a higher concentration, a higher percent. And we're going to call that our concentrate. So instead of a serum, which is a pure substance like blood or urine or a pure medication, we're dealing with a concentrate, which is basically it's a medication that's already been diluted down once. And we are going to dilute it to a lower concentration. So if you recall, we had that formula for solutions from the last unit, where the amount of that active substance was equal to the concentration times the volume. So if I have 200 milliliters of 32% solution, the amount of active substance in that is going to be my concentration of 0.32 times my volume of 200 milliliters. If I multiply those out, that gives me 64 milliliters of that active substance, whatever that medication is that is in that solution. Well, what if I perform, let's just do this. It's simpler than that. Let's just say we're going to add 600 milliliters of saline to that. Now remember that saline is just sterile water. It has no medicinal value. So how much active substance have we added to this? 0. 0 milliliters of active substance. But we have changed the total volume from 200 to 200 milliliters plus the 600 we added is now 800 milliliters. What is that final concentration? Well, it's the active substance. It's still 64 milliliters equals our new concentration times our new volume, which is the 800 milliliters. So to solve for the concentration, we divide by 800. Yeah, we had the 200 milliliters of 30. Was the 64. Yes. Yep. The new total volume. Yeah, we added 600 milliliters of water. So there was no medicine added, no active ingredient added. So, yep, so we're trying to find the concentration. So we divide 64 divided by 800. Gives us 0.08. It's our new concentration. So that's 8% is our new concentration. So now let's look at this in terms of a dilution. We had 200 milliliters of that 32%. We added 600 milliliters of saline. What dilution was performed here? Remember, the dilution was serum over total. Well, here, since it's not a serum, it's a concentrated solution, it's going to be concentrate to total solution. So remember, the concentrate is the amount of the higher concentrated solution, which is 200 milliliters. What's the total solution? You got it, the 200 plus 600. So that's 200 over 800, which of course reduces to a 1 in 4 dilution. So that's our dilution. Well, if we compare our percents, the 200 milliliters was at 32%. After we diluted it, what did we get for the percent? 8%, right? That's what we found up here. There's a relationship between those percents and the dilution. We have a 1 in 4 dilution. Our ratio of percents, 8% to 30%, or 32%, is the same ratio as our dilution, a 1 in 4. Now, this is a little bit confusing, and let me show you why. Because our dilution, the 1 represents the volume before we diluted it. I'm going to call that volume 1. The 4 represents the total volume after we diluted it. I'm going to call that volume 2. On the other side, the 8% represents the concentration after we diluted it. That's the second concentration. We'll call it concentration 2. And the 32% is the concentration before we diluted it, concentration 1. So you'll notice these don't necessarily match up. We're used to having in these proportions, whatever goes here has to be related to what goes here. Well, here that second one is flipped over. The reason for this is what's called an inverse relationship. We'll talk about that more in Unit 4 in the algebra portion. For right now, we just have to use this formula. And it does make sense. We know that the concentration has to be lower after we dilute it, so we match that up with a smaller number in our dilution. So let's look at it this way. A 63% solution is diluted 2 in 7. Find the new concentration. Well, here we don't have the volume of that original 63% solution. We just have the percent. But as we saw up above, we don't need that volume. It's a 2 in 7 dilution. The 63% is the concentrate that's going to go on bottom because we know the new percent is going to be smaller than it. If you dilute it down, the concentration goes down, the percent goes down. So we're going to find that number by cross multiplying and dividing. 2 times 63 divided by 7 gives us 18. It's an 18% solution after we dilute it. Well, we had the 1 in 4 dilution. We could have just put the 32 here, did 1 times 32 divided by 4. But what we did is we used the total volume, since I gave you the total volumes. We had 64 milliliters of concentrate in that original solution. So the new volume was 800, so we divided by 800 to get the 0.08, which is 8%. Another application of this concept would be how much saline should be added to 120 milliliters there we go, 120 milliliters of 18% solution to dilute it to 4%. Well, we need to find the dilution. Remember, the dilution is the ratio is equal to the ratio of percents. So whatever our dilution is, the concentrate over the total, that's got to equal the lower percent, the 4%, over the larger percent, the 18%. Well, if I reduce that ratio of percents, of course, the percent cancels out, 4 over 18, both divided by 2 to give me a 2 over 9. So that means we're looking for a 2 in 9 dilution. I want to know how much saline, right? I know how much of the concentrate I have. The ratio of concentrate to saline is 2 to 7. Remember from that problem we did to introduce it? If the ratio of concentrate to total is 2 to 9, the concentrate to saline is 2 to 7. We put in the 120 milliliters for the concentrate, cross multiply and divide. 7 times 120 divided by 2 is, was that 420 milliliters? This is our dilution that we got from the ratio of percents. So a 2 in 9 dilution is always concentrate to total. Well, we had the amount of concentrate, but we're not looking for the total, we're looking for the amount of saline. So we change that to the ratio of concentrate to saline. There's still 2 parts concentrate. If there was 9 total and 2 of those parts were concentrate, the other 7 parts are saline. No packets, no, just the homework out of the book. Yeah. Any more questions on that one? Okay. Now, that's one way we can work with these solutions to dilute the concentration. But we'll notice we have that formula. Volume 1 over volume 2 equals concentration 2 over concentration 1. Well, from that formula, we can actually readjust to create a little bit simpler formula to use. It's what we call our change of concentration, or sometimes called the concentration adjustment formula. And what we're doing is we're just simply cross multiplying this proportion. On this diagonal, we have V2 and C2. So that's C2 times V2, concentration 2 times volume 2. And on this diagonal, we have concentration 1 times volume 1. Now we typically write that formula the other way around. C1 times V1 equals C2 times V2. Now if you look at this formula, it makes sense because concentration times volume, if you remember back to our solution mixtures, the amount of active substance is equal to the concentration. I'm just going nuts on me here. The concentration times the volume. So if all we've added is water, the amount of active substance hasn't changed. So that should be the same before and after we've added the water. So we can use that formula there, C1V1 equals C2V2, to do the same thing we've been doing with those dilutions, just a little bit quicker. So for example, let's say we start with 180 milliliters of 42% solution and dilute to 14%. Find the new volume. Well, again, it's C1V1 equals C2V2. The original concentration and volume are right here, 42% and 180 milliliters. Now, because of the way this formula is, we have a choice. I can either put that concentration in as 0.42, or I can leave it as 42. As long as I do the same to both concentrations. To make it easier, I'm going to leave it as 42. So my concentration is 42 times my volume of 180 milliliters. That's the before, the first concentration and volume. My second concentration and volume, what do I actually know? The 14% is the second concentration. I am looking for the new volume, V2. Now I should note, remember that 2 is not really a number. That's just indicating that that's the second volume. So we can't do anything mathematically with that 2. So to solve this, we do 42 times 180, which is 7560, perfect. Equals 14 times V2. And now we solve that by dividing by the 14, which is what, 540? Equals V2. So our second volume is 540. So that's 540 milliliters because the first volume was in milliliters. So the new volume is 540 milliliters. Yep. Yeah. Smaller volume has to have a higher concentration to have the same amount of medicine in it. Older. Yes. Now, similar to that, let's say that we have 240 milliliters of 56% solution is diluted to a total volume of, let's go 960 milliliters. Find the new concentration. So again, I tend to always write out the formula. C1V1 equals C2V2. And I usually let C1 and V1 be the solution that I know both the volume and the percent for. That's this one here. We have 240 milliliters, 56%. So that's 56 times 240. On the second side, the second solution, I know the volume, I'm looking for the concentration. So C2 is what I'm trying to find. My volume is 960. So I will multiply 56 times 240. Is 13,440 equals C2 times 960. And now we solve by dividing by 960. Which gives us 14 as C2. So C2 is 14%. Yes. Remember, concentration is finding a percent. Yep. Now, just kind of a side note. What is the maximum? What is the largest value of a concentration? Yes, 100. 100% means it's pure. If you're doing any of these problems and you ever come up with a percent more than 100%, you know there's a problem. Similar to those, related to those, we might ask, how much saline? No, the battery in my pen is going bad. I'm gonna have to replace the battery on break because it's not writing here. How much saline should be added to 60 milliliters of 80% solution to dilute it to 16%. So again, C1V1 equals C2V2. We have 60 milliliters of 80%. So that's 80 times 60. We want it to become 16%. So that's 16 times V2. So now we go to solve. 80 times 60 is 4,800. Well, you could have done, you don't have to. You could have done 16 and you would use that as V1 and 80 times 60. You could do, if you switched it around and did volume times concentration, that's fine as long as you do the same for both, as long as it's consistent. So anyway, now we're going to divide this by the 16 to divide that out. That comes out to be 300. So my volume 2 is 300 milliliters. Now I have to be careful. Is that what our question was asking? It wasn't asking for the total volume. It was asking how much saline. So we had 60 milliliters, and we're going to be going up to 300 milliliters. The difference has to be saline. So we add 240 milliliters of saline. Does that make sense? Well, the original solution. It wasn't the active ingredient, it was the total original solution. But when we diluted it down, in order to dilute it down, we had to increase it to a volume of 300. So what takes us from 60 to 300, all we can add is saline. So the difference in volume is made up within saline. Yes. I'm going to have you guys try one. Find the new concentration after 240 milliliters of saline is added to 120 milliliters of 36% solution. And there is one little bump in there that you need to see. Let's take a peek here. So like I said, I always start out with the solution that I know both numbers for. We have 120 milliliters of the 36% solution. So that concentration is the 36%. Volume's 120 milliliters. On the other side, what do I know? The answer is not the 240 milliliters. It's 240 milliliters plus 120 milliliters. So that means we have a new volume of 360 milliliters over there. So C2 times 360. So now, yes, we do the 36 times 120, which is 4320. Oops, put my desk. Then we solve that by dividing by the 360. So what do we get there? 12%. C2 equals 12, so that's 12%. What do you think? I just said the 4320 divided by 360. Oh, sure. Right there? You bet. Yeah, the key to these is to remember that these volumes are total volumes, not just the amount of saline. The volume of saline is a part of one of those, but it's not one of them. Just like with the dilution, if you're given the volume of saline, you've got to add something to it to find a total volume. Now, can somebody tell me what dilution was performed here? There's actually two different ways to figure out what the dilution was. Yeah, I could either compare the total volumes of 120 to 360, that reduces to a 1 to 3. Or I could compare the concentrations. 12% to 36% gives me a 1 to 3. So it is a 1 to 3 dilution, or 1 in 3 dilution. Oops. Let's do this. I'm going to have you guys try one more. Find the amount of saline to add to 30 milliliters of 72% solution to dilute it to 4%. I'll give you guys a couple minutes on that. So let's see how you're doing. We got C1V1 equals C2V2. We have the 30 milliliters of the 72% solution. So C1 is the 72 from the 72%. V1 is the volume of 30 milliliters. C2, we want 4%. We're going to be looking for that second volume. So 72 times 30 is 2,160 equals 4 times V2. And we will divide that by 4 to get 540 is V2. So 540 milliliters is not our answer. That's our total volume. Remember, how much we're asked how much saline to add. Well, we already had 30 milliliters. So to get from 30 milliliters to 540, we subtract to get 510 milliliters of saline to add. Yes. Yeah, the biggest thing always, I always tell people, once you have solved an equation and calculated a number, go back and make sure it answers the question being asked. Okay, it's 9:17. Rather than jump into another topic for 3 minutes, let's go ahead and take a short break. Let's come back at 9:27. We'll start lecturing then. Yep, they're getting settled in there. Okay, so the examples we just did, let's kind of step back and do some other examples and see where we stand. So let's say that we have after 150 milliliters of saline is added to a solution, the new solution is 24% and 200 milliliters. Find the original concentration. I'll give you guys a minute to try that one. Okay, so let's take a peek at it. So it doesn't really matter which one is solution 1 and which one's solution 2. It really doesn't, as long as you keep them together. So the 24%, 200 milliliters, I can make that solution 1. It doesn't matter. So concentration of 24% times a volume of 200 milliliters. The tricky part comes in the second one. Find the original concentration. So I'm looking for the concentration. What goes in for the volume? There we go. We have 200 milliliters after we've added 150. So we subtract 150 milliliters of saline. The original solution was only 50 milliliters. Put 50 milliliters there. We will multiply 24 times 200, which is 4,800. and then we'll divide by the 50. Get 96%. So yes, that new concentration, or the old concentration, was 96% before we diluted it down. Less of it, more concentrated. Yes, smaller volume, higher percent. Think of it this way, it's an inverse relationship between volume and concentration. Also put the N in there. An inverse relationship. If the concentration gets larger, the volume gets smaller. This is if you keep the amount of active ingredient doesn't change. For the concentration to get larger, you have to have a smaller volume. If the concentration is getting smaller, that means the volume is getting larger. Yes. Yes. Okay, so let's look at another problem with our dilutions. This might be a little bit of a throwback here, so brace yourself. A sample of 40 milliliters of urine is tested. After being diluted. The diluted reading is 310 milligrams per deciliter. The calculated actual reading, or actual level, is 930 milligrams per deciliter. How much saline was added to the sample of blood? I'm going to give you guys a couple minutes to work on this. Yes, that should be urine, not blood. So I warned you this one might be a little bit of a throwback. We have a diluted level and an actual level. And if you recall, first example we did today involved diluted levels and actual levels. Our diluted level is 310 milligrams per deciliter, and our actual level is 930 milligrams per deciliter. That can be reduced. Milligrams per deciliter cancels out. Both of those divide by 310, which gives us a 1 in 3. That is a dilution. So we have a dilution of 1 in 3. We can use this in one of two ways. I tend to go back to basic concepts. So I would use that 1 in 3 dilution like this. That's a 1 in 3 ratio of, in this case, urine to total solution. I would change that to a ratio of urine to saline. So it'd be a 1 to 2 ratio. If there's 3 total parts and 1 is urine, the other 2 are saline. And then I would have, we had, or is it 40 milliliters of urine. And I could cross multiply 2 times 40 divided by 1. 80 milliliters of saline had to be added to it. The other way we could use this, even though this is just 1 to 3 rather than 1 milliliter to 3 milliliters, there's no units on it, we can still use that as a ratio of volumes. So we could use that in our V1C1 formula. The problem is, what is our concentration? Our concentration of urine is 100%. So we end up getting a percentage, which is going to be tougher to work with. I hesitate to show you that because I don't want to confuse you. But if you want to just kind of shut it off right now, if this makes sense to you, you want to kind of shut me off for a second. Our ratio of volumes here is 1 to 3. The one volume is at 100%. This concentration, if I solve this, that's going to be at 33 1/3%. Well, to figure that out, then we'd have to go back to our active ingredient formula. So 1 times 100 divided by 3. So you'd have to go through now the amount of active ingredient equals your concentration times your total volume. You get the total volume off of that because you have the 40 milliliters of active ingredient. Yeah. So you get your total volume and you can subtract to get the saline. Personally, I prefer to just stick with the regular dilution. Okay. We've talked about these percent solutions. Let's take a look at where they come from. So what we're really looking at is solution concentrations here. What do they mean and how are they calculated? Well, I want to start out with the simplest type of a solution concentration. And that is what's called a weight in weight solution. Now, I don't know if you guys went over in the last unit the difference between weight and mass. We tend to really blur the lines between weight and mass. Weight is the force of gravity on an object. Mass is the amount of matter in the object. In other words, literally how many particles are in that object, how much stuff is in that object. Now they seem like, well, that means pretty much the same thing. Something with more matter in it, something with more mass is going to weigh more, and that's true. The difference is how they're measured. Weight is measured against a spring. A spring will stretch a proportional amount depending on how much force is applied to it. So you have that spring and there's an indicator on that spring as to where it's resting at. And the reason it's called a scale is because there's a number scale that indicator will point to. If I put an object on there, it's going to stretch that spring and it's going to pull that indicator down. The distance that indicator moves indicates the force being applied and measures the weight of that object. Mass is measured with what's called a balance. So we have the object we're trying to measure on one end, then we put known masses on the other end. And when it balances, whatever this known mass is the mass of the object. Well, you might say, well, doesn't that pretty much do the same thing? Well, here's the difference. Let's say we go to the moon. On the moon, there's a lot less gravity, isn't there? Actually, approximately 1/6 the gravity of the Earth. So that means this is going to pull down less, and that indicator is going to move a lot less distance, about 1/6 the distance. Here, however, yeah, the pull on that object is going to be less, but the pull on the known mass is going to be less as well. The same mass is still going to balance it. So mass does not change. Weight depends on gravity. Why do I bring that up? Well, we call this a weight in weight solution, but then we go and measure it in milligrams and grams. Problem is grams is a unit of mass. In the metric system, there's a unit of weight called a Newton, but we use that in science and engineering, but we don't use that too much in everyday application. We're blurring the line between weight and mass. On Earth, though, the force of gravity is relatively constant. There's like a 7 or 8% difference in gravity between the North Pole and the equator. And what that means is somebody who weighs 200 pounds at the North Pole might weigh like 192 pounds at the equator, or actually a little bit less. So since gravity is relatively constant, we tend to just kind of sloppily switch back and forth between weight and mass. I just wanted to bring that up because even though we're calling this a weight and weight solution, we're using mass units. We're using milligrams and grams. So anyway, there's an abbreviation. We usually do W/W solution. So let's find the concentration. If 30 milligrams of serum of medication is in 150 milligrams of solution. Now you will notice this is the amount of serum. This is the total solution. Similar to our dilution again. It is always serum to total. So that's 30 milligrams over 150 milligrams. Now the units used here, the milligrams, doesn't matter what unit we use. We could use milligrams, we could use grams, we could use micrograms, we could use grains. Whatever unit we need to, we can use there as long as both of them are the same. And now we're just going to turn that into a percent. A percent is always out of 100. Now we'll cross multiply and divide. Milligrams cancel out. 30 times 100 divided by 150 is 20. 20 out of 100, so that is 20%. The 20% solution. Well, percent always means out of 100. So 20 out of 100 is 20%. Now, if you're used to doing the rate method, no, you don't have to. If you're used to doing the rate method, you can. Just a little extra, a few extra steps. Yep. Now, if you're used to doing the rate method, what you can do is just do 30 divided by 150 is 0.2, and 0.2 is the decimal form of 20%. And I don't know which way you guys worked with the most in the last couple of units. You're looking for the concentration, yes. Now, the nice thing about doing weight and weight, and like I said, it's technically mass and mass, is that mass and weight are what we call additive. If here I gave you the mass or the weight of the serum and the weight of the total solution, but I could give you, let's say I ask you find the weight and weight concentration if 50 milligrams of serum is combined with 300 milligrams of saline. Well, remember our percent, our concentration always goes off of serum over total. Do we have the amount of the serum? 50 milligrams. Do we have the total amount? No, but we can do 50 milligrams plus 300 milligrams. So that gives us 50 over 350. Now, are you guys used to doing the equals, blank over 100? Or are you guys used to just dividing it out, getting the decimal and moving the decimal? Just the decimal? So I don't know what you guys stressed when you guys did percents earlier in the course. So we just do 50 divided by 350 is 0.142857143 approximately, right? Yeah, it's not as tough as it looks. So we got to move the decimal point. We'll round that off to a 14.3% solution. Math is all about patterns, and once you start to see the patterns, the calculations are pretty simple. It would take me a long time to explain the patterns. You got to remember, I've done this stuff every day of my life for like 18 years now. So. Any questions on that one? Well, another option is called a volume in volume solution. Often abbreviated just V/V. We have to be careful with volumes. The reason I say we have to be careful with volumes is this. This is kind of a side note here. If you add 50 milliliters of salt to 400 milliliters of water, do you get 450 milliliters? No, try it at home sometime. It doesn't add up. You'll end up with like 430 milliliters. What happens there? It dissolves. Yeah, well, what happens is we have water particles in the water. And water particles are actually kind of like long chains. So I'm kind of drawing them weird here. But from your chemistry, you know that those particles actually do have some space between them. And the salt particles fit in those spaces. Yeah, the weight would combine. If the mass of the salt and the mass of the water have to add up. Mass is always conserved. It's always additive, but volume is not necessarily so. So the salt can hide in there. What's that? If that were 50 milligrams and 400 milligrams, it has to be 450 milligrams. The weight can't hide. Because even though the salt's hiding in those spaces, the weight of the salt is still there. Now, I'm saying that as a side note because it's not going to affect what we do in this class. What we do in here, we are going to assume that we have water-based solutions. What that means is when we're doing volume and volume, and it's mostly true when you're doing volume and volume, is you have two liquids, a liquid going into another liquid. And for the most part, liquids don't dissolve into each other. The exception is alcohol will dissolve into water. So if you add alcohol in the water, the volumes won't add. But we're going to avoid that example for this class because the math gets kind of difficult. Alcohol dissolves in water just like salt dissolves in water. Alcohol will hide between the water molecules. Yeah. So what we do in here, we are assuming that we're using water-based solutions. And since the base is water, when we combine them, they will add volumes. Does that make sense? Okay. So really it comes down to having particle sizes that are close to the same. So if we have find the concentration, find the volume and volume concentration. For a 600 milliliter solution that contains 150 milliliters of serum. And just like I did here, for the most part, when we're working volume and volume, I'm going to give you examples where I have the amount of the serum and the total volume. So it is just like with weight and weight, it's going to be the volume of serum to the total volume of the solution. I have the 150 milliliters. I have the 600 milliliters as my total volume. If I divide those out, I get 0.25, otherwise known as a 25% solution. Okay, next. Yeah, if they're asking for a concentration, they're generally asking for it to be a percent. Yes. Yeah. Yes. If you did it like this as 150 over 600 equals blank over 100, if you were to cross multiply and divide there, 150 times 100 divided by 600, that gives you 25. So that is the 25%. Yes. The final is called weight in volume concentration. Weight in volume, abbreviated W/V. To understand weight and volume, we go back to water. And I don't know how much of this you went over in the last unit when you talked about your units, your metric units of measurement, but did you guys discuss the meaning or the origin of 1 gram? Okay, 1 gram is defined to be the mass of 1 milliliter of water. That's what it was defined to be. So 1 milliliter of water. So now, since most of the solutions we work with are mostly water, have densities close to water at least, about 1 milliliter is equivalent to about 1 gram. So when we're doing a weight in volume concentration, the weight has to be in grams and the volume has to be in milliliters. Find the weight and volume concentration for 250 milligrams of medication in a 200 milliliter solution. Well, recall, the medication or the serum has to be measured in what units? Grams. So we're going to take our 250 milligrams and we have to convert it into what? Grams, which would be how much? That is correct. 3 spaces over. That's 0.25 grams. So then we need our total volume, which is going to stay milliliters. So that is 200 milliliters. Because it has to be. Because remember, a gram is equivalent to 1 milliliter. Yes. Now it does get confusing because you want to link milligrams and milliliters because they're both milli, but it's 1 gram to 1 milliliter. So if we divide that out, you get 0.00125, or that is 0.125%. 250 milligrams in only 200 milliliters of solution sounds like a lot of medication, but it's not. That's an extremely small concentration. You divide this out and you get that. That's a decimal or a rate. You do have to move it over 2 spots or times 100 to make it a percent. The other way you could think about it is like this. 0.25 grams over 200 milliliters. And you have to do that as equals blank over 100. And when you cross multiply and divide, this is 0.125. Yes. Three spots, yes. Yeah, if you look at our metric chart, to get from milligrams, I should put grams here, not meters. This is a percent here. So percent is out of 100. So you have to move it, to change a decimal into percent, you move 2 places. Okay, that's okay. I mean, it's confusing when why is it 2 sometimes and 3 another? Yeah, this is the units. From milligrams to grams is 3 spots on our metric chart. So we have to move the decimal point 3 spots. But yes, the percent is out of 100, so that's 2 decimal places. These weight and volume solutions tend to be the ones where it's a powder medication in a liquid or in water, typically. The reason they use the weight and volume is because of what we had discussed before. When you add a powder to a liquid, the volumes don't add together. So they use that weight and volume to kind of keep you from trying to use that. So here's the question. How much medication? Notice I'm calling it medication instead of serum when we talk about weight and volume as well. Serum is usually referring to a fluid medication, or the medication itself in this case is powdered. So, I mean, you could call it serum and it wouldn't be a horrible mistake. But yes, it's still the active. Medication and serum is still the active part. So how much medication is in 120 milliliters of 8% weight in volume solution? I'm gonna give you guys a minute, see if you guys, what you guys come up with there. Okay, so we have this weight and volume solution. It works easier for me if I do the 8% as 8 over 100. The 120 milliliters goes on bottom. That's my total solution. To find the amount of medication, that's going to be this number up here. I'm going to cross multiply and divide. 120 times 8 divided by 100 is 9.6. Here's the tricky part though, 9.6 what? Grams. Very good. It's already in grams. What we get there is in grams. If we have the percent and we're going backwards, what we're going to get is grams. Then you'd have to move the decimal to make it 9,600. It doesn't. Just how much. On a test, I would actually put what units I was looking for by the answer if I was looking for a different unit. Okay, any questions on that constituting concentrations of solutions? Or too many to ask? Like I said, the biggest thing is just to remember when it's the weight and volume, it has to be grams over milliliters. The other ones, the weight and weight and the volume and volume, you just have to make sure you have the same units. Let's look at these little things. Syringes. The key to understanding a syringe is learning how to read a scale. Now you'll notice I left this one blank because we're going to fill in a scale on it here in just a second. Now first, they do have to be marked. We're going to assume that all these are marked in milliliters unless I give you otherwise. No, you don't. It's just a blank little tool that I have to use for the demonstration. I can post a blank version of it on Blackboard if you would like. Okay, I'll do that for you. So we have a worksheet of a syringe like this. If it is labeled in milliliters, 1, 2, 3, 4 like that. To read the syringe, we need to figure out what each division is. In other words, we need to figure out what does that stand for. To do that, we avoid starting out at the beginning of the syringe because often at the beginning of the syringe here, because it's tapered, the first couple of markings might be kind of hard to see. They might actually be off the taper. So we usually don't start at the very beginning. We'll usually go with 2 marked readings. So we'll go from here to here. What volume is indicated in that range? Well, that's 2 milliliters minus 1 milliliter, which is 1 milliliter. Next, we need to figure out, well, how many divisions are there? Well, from the 1 to the 2, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions, aren't there? So divide by 10. 1 milliliter divided by 10 is 0.1 milliliter per division. So that's telling us each division on here is 0.1 milliliter. So now if I fill this syringe, hopefully this, let's see what that does. Oh, that turned out okay. So I fill this syringe and try to read what that level is. Well, I go to the nearest marked spot, the last marked spot that I've gone past. That's 3 milliliters right there. Each division past that is 0.1. So this is 3.1, 3.2, 3.3 milliliters. In this case, because it was just a tenth of a milliliter, or 0.1 per division, it was pretty easy to count up. Another thing we could have done is we could have counted 1, 2, 3 divisions. We could have taken 3 times 0.1 to give us 0.3, and we would add that to the 3 milliliters. Now, the reason I put that out there, that seems like it's a lot more work, but there are going to be times where you may have to do it that way because the amount per division might come out to a strange amount. So let's mark this one. Bless you. Bless you again. So this one here is marked cc's 1 to 2. First of all, what's the difference between a cc and a milliliter? Nothing. There's the correct answer. 1 cc is equal to a milliliter. 1 milliliter is defined to be a cube that is 1 centimeter by 1 centimeter by 1 centimeter. 1 cc stands for cubic centimeter, and a milliliter is defined to be a cubic centimeter. So now let's go to finding what each of these divisions are. From here to here, that's from 1 to 2 again. 2 milliliters minus 1 milliliter is still 1 milliliter. The difference now is how many divisions are between there. From here to here. Nope, that volume doesn't, we don't know what that volume is, but it's part of whatever is marked here. That has no volume of its own. Because I don't want to start here because the markings at the beginning of the syringe might not be true. Because the taper on that syringe, the first couple of markings may not show up. What we're doing is we're just going between two marks. We could go from 3 to 4 if they were on there or whatever. We just want to know marked markings so we know exactly that is exactly the start and the stop point. Otherwise, up here, we don't know exactly where the start point is because of the end of that syringe. Just like if you look at a ruler, sometimes the corner of the ruler can be worn off. The first couple of markings can be unclear. Yeah. Yeah, so we're going from 1 to 2, which is a 1 milliliter range. Now I'm going to show you a shortcut. We see that there's 4 clear spaces here. I'm just going to count 1, 2, 3, 4, 5. And there's 4 of those sets of 5, which is 20 divisions. So 1 milliliter divided into 20 divisions is 0.05 milliliters per division. So each division on this syringe, on this scale, is 0.5 milliliters. So let's fill up our syringe. 0.05, I should say. So it's 0.05 milliliters per division. So now here's my closest marked. That's the 1 milliliter. How many divisions have I gone past? Well, we counted up. This is 5, 10, 15. That's 16 divisions. I could count up 0.05, 0.1, 0.15, 0.2. That gets kind of clunky to do. But it's 16 divisions times 0.05 milliliters per division. That multiplies up to make 0.80 milliliters. Plus my 1 milliliter, that's 1.80 milliliters of fluid in there. That's a good question. Do we have to put the 0? Mathematically, the 0 doesn't mean, numerically, the 0 doesn't mean much. When it comes to measurement, that 0 does mean that this was measured down to 100th of a milliliter, and it happened to come out closer to 80 hundredths of a milliliter rather than just 8 tenths. There's a long conversation. You guys talked about significant digits a little bit, and that's what it comes down to. The significant digits are telling you about the precision of the measurement with the measuring device that was used. That'd be the difference between using this syringe to getting 1.8 milliliters and using this syringe up here. You could still get 1.8 milliliters, but that only goes to the 10th of a milliliter. Which we're going to cover these syringes more next time we have class. But one quick point I want to make here. If I have 2 different syringes, let's say I need a dosage of 2.3 milliliters. We'll use a little bit of an extreme example here to prove a point. Would I want to use that syringe? Or would I want to use this syringe? The smaller. Why would I want to use the smaller syringe? It's more, yeah, actually more precise is the technical term, but you had the right idea. We could find 2.8 milliliters here. It would be just right there, it would be 2.8 milliliters. The problem is, the difference is all my syringes here are the same size, but in reality, a syringe that has the numbers going up that quickly is probably a very wide syringe, like this. A syringe that has the numbers relatively spaced that only goes up to 4, that's probably a relatively narrow syringe, like that. Well, when I go to move this plunger in and out to get that 2.8 milliliters, am I going to end up exactly on the 2.8? No, I'm going to be off a little bit. So let's say this is what I'm shooting for 2.8 right there. And my plunger ends up right there. I've missed by a little bit. 2.3, I'm sorry. I don't know why I was thinking 2.8. Dyslexic moment, I guess. But anyway, 2.3. So that green mark is where my 2.3 milliliters was. So I want to be on that, but I end up where that maroon mark is where my plunger ends up. Of course, now words are going to crap out on me. Anyway, we'll go back here to my other document, maybe.